Welcome everybody to today's Sendo Reliability webinar. This is Fred Schenkelberg, and today I'm going to talk about ORT, which is, I think, more commonly what we say when we think of the ongoing reliability testing. And just by way of background is I did, I don't know, close to 200, 250 different organizations reliability assessments over my career. And I've seen some variations of ORT that I would probably call HACCP or stress screening or burn-in, which I don't think is ORT. And I also saw a whole bunch of others that, even though they called it ORT, it really wasn't very useful. So I've seen plenty of good examples, one really wonderful one, and a handful of really horrible ones. I'm going to relate some of those as a way to say this is what it is or should be and isn't, is by way of definition. But then we'll get into some of the basics and some of the thoughts about that, of how you go about doing it. And I'm going to say it right up front, and I'll probably say it a few times as we go through it, is that there isn't one formula, there isn't one process, there isn't a, standard that says if you follow the standard, you are going to be okay. And there's a whole lot more to it. And it's like any test plan, it actually has to have a rational chance of actually adding value. I think Chris Jackson often calls it is, if you can run a test and you can admire the problem, but unless you actually do something to actually catch changes or modifications that happen in your processes as you're producing products, and then do something to resolve them, you're just admiring the problem. You're having a good old time in the lab, but you're not actually adding any value. So I'm going to try to really distinguish what are the elements that make up a good ORT, at least in my opinion. All right. So you're in production, you're making something, right? And you've gone through the design process, you've handed it off to manufacturing or your contract manufacturer, and you're producing products, and they're starting to go out the door, and you get happy customers, and all is good. But then something changes. And all of you that have any experience whatsoever, even 10 minutes within a product development cycle, is, well, changes will happen. There's absolutely no doubt in anybody's mind that a vendor is going to change their product, their formulation, or the process will change, or the weather outside will change, and that may affect your process. Raw materials may have a slightly different additive than they used to have in it. On and on and on. Change will happen. And many of those changes really don't matter much. They don't, if the product is designed well, it's robust enough, it'll survive, the slight changes and slight formulation changes and slight temperature changes and so on. Yet, as many of you know, is that every now and then you get a change and they say, oh, we didn't think it would affect you. And it does. And now all of a sudden you can't create a product that actually works. And or worse, it creates latent defects that get out to your customers. And that's kind of why we do a variety of different testing at the end of production lines. It's very, very common, especially in electronics, to take that circuit board and put it on a bed of nails or some other technique to say, well, was it wired up correctly? Does it have all the components there? Is the ICs and all of the logic circuits, are they working? And so we do a range of different testings, mechanical systems and so on. Is, making a motor, does it spin up correctly? Does it have shorts in it? Is the insulation sound? Is it aligned? On and on and on. We often want to know and make sure that the products we're ready to box up and send to customers actually work. And a lot of that kind of testing at the end of the line is, did we add all the parts? Is Did we miss something? Is something not there? If the on-off switch is missing from the back of your computer, well, it's kind of not well, it is possible, but it would take more skill than I care to venture into to get it started. It should have an on-off switch of some sort. And if that just was overlooked and it was boxed and shipped out, you would have an unhappy customer. It's like receiving a car without a steering wheel. Well, it's probably a bad analogy. But the idea is that we often look for and detect production or supplier problems, and we do it pretty quick. We don't want all of our production to be sitting around in the factory for another 3 or 4 months while we analyze whether or not they're going to survive, or whether they're going to live long enough. It's usually pretty quick. We make a quick check to see if it's wired correctly, it was set up correctly, all the parts are there. We put it in a box and it's on a truck, usually that day. In some industries, it takes a bit longer. But the idea is that if you finish producing it, it's now just a piece of inventory and it costs you money. And so we want to get it out to customers. The other option of detection, is it going to last long enough, is one that's kind of a silly example, but let's say we do a life test on every single unit we produce and we find out how long they last. Well, that would be great. It would be really bad for the customers because they would, if they get a product that's going to be 5, 10, 20 years old, whatever the life of your product is, and it will fail pretty quickly because you've consumed all of its life and in testing it and stressing it. And so it's not terribly useful to do a test on every single unit that you produce to see if it's going to last long enough. And there's all kinds of variations and surrogates and everything else. And but we'll get into what ORT is here. So the idea is that we want to know if in this detection phase are the changes that will occur in our production process, in the environment, in the raw materials and components that we bring into the assembly, which of those changes significantly reduce the durability of the product? And that should be obvious that we would want to know that. If we're claiming that it's going to last 5 years and it doesn't, even though we tested it and did all the design work and so on, is that it's that risk that one of the changes will cause a difference. And so that's why we do ORT, and not all the time, but we'll get into that. So what do you guys do? How many of you do ORT or some variant of that? Do you do HASS, highly stress screening, or HASA, or stress audit, or burn-in? I hope that should be a whole nother webinar. MOST, or some other variant of some set of acronyms. How do you detect if your product is good or not for the duration, for the long term, before it goes out? And I do know a good number of people don't do ORT of any kind. And that's okay. That's a viable option. So what do you do? What kinds of stuff do you do to make sure your products in production are equally reliable as what you expect them to be? Well, I'm not seeing a flurry of examples here. So, well, maybe this will give you some background. Today's presentation will give you some insights and conditions about what you should think through before you go do it and why you would do it. Seen it done before, Maximilian saying, and cheap to make, large quantity. Some of the lot was tested and then scrapped. Yeah, okay. So yeah, you're doing a life test on something usually means you can't sell it. It's pretty common. All right, let's get into this acceptance testing. Okay, now run ALT. Andre's talking about combined thermal stress, drop, and vibration. Interesting. Let's see how that goes. All right. A couple of folks are doing things. All right. Well, let's see how what you're doing matches up to what, at least the concept I think of when I think of ORT. So let's go through a couple of examples as a way to define what it is and isn't. And I'll start with the good news first, just because that was the way I was feeling when I was writing this up. Some of you have heard the story. I used to work at Hewlett Packard, and one of the roles I had early on was working with inkjet printers. And I and it was and still is a big business for one of the least one of the variants of HP that exists today. And the print heads, the actual item in the product that actually spits the ink out and makes the printing of inkjet printing work, that division in Oregon, and I got the chance to see it one day, had this massive room with racks and racks and racks of printers. And it wasn't just one style of printer, it was the variations of printers that could use the various generations of print heads that we had available. And there must have been 1,000 printers in there, maybe more. And they weren't testing the printers per se, they were testing the cartridges themselves is what their primary setup was. But in doing that, they also were running them inside printers that then they also monitored for problems and so on. And there was a couple, like 2 or 3 people, and per shift, because these things ran 24/7, that would, their full-time job was to monitor the systems and initiate the failure analysis when something was found off or problematic or not working or it stopped working. But primarily they were putting paper in these things. They were refilling the paper trays on these things on a regular basis. And one of the things they did is they had a 6-week rotation. So a printer and its inkjet printer head would go into testing, would be sampled from that week's production, and then would go into sampling. And it would run some variant of some use case. And I think there were 5 identified different use cases, from very heavy full page, full color to, very sporadic, once in a while print off of black and white. And there was a number of different scenarios that the organization had identified as ways people use the products. And they ran them in real time, stress conditions. They didn't accelerate anything. Some printers were idle for a week, and they do print 2 pages, and then they'd sit idle for a week and they'd print 2 pages. Whereas others would print maybe 500 pages per day of full color ink. And the scenario they told me that was a small brokerage house that was printing flyers for their different listings. In the US, you often see a little basket or tray, kind of as a sales page, was maybe a handful of photos on it and some fancy words about how it's charming or this, that, or the other thing. And as a handout for people that are shopping for houses, and they would have the realtor's contact information and some details about the house and so on. And there was a handful of other use cases. And then they would, so at the end of, as the product got started, they would take, I don't know, it was close to 100, 150 samples and put them up on test. And they would do that every week. And so at the end of that, you had what, 600, almost 1,000, say 900 printers running. Now, some of the sample size was because, one, they were trying to detect very small probability of failure items. And so that you need actually a good number of samples to even have the chance to catch a very 1 in 1,000 type problem, or even less than that. But it's a trade-off. They could have taken way more printers and detected even smaller issues, but they found that kind of a sweet spot in their operation, that this was able to detect with 1,000 printers sampled over a 6-week rotation. And then they kept that going. and there was a defined endpoint for it too, is when they would say, all right, this product line is only expected to be in production for 6 months. So I think they only did it for 2 or 3 months in this ORT example. So it wasn't unlimited sampling and unlimited samples, but they had thought through what a combination of things, and we'll get into some of all these factors, but how much space they had, how many variants they had, how much, what level of failure they were trying to detect. And since they were running it in the full product and running it in relatively normal conditions, it wasn't accelerated at all. So if it worked for 6 weeks, it just worked for 6 weeks. That was it. And then those units would be scrapped or used for other purposes, but they weren't sold. One thing that was striking is that they were very, very sensitive to any issue. If it sounded weird, which was hard to do. I don't know how they detected that, because when you got 1,000+ printers rattling off paper in random ways, even though they tried to make the printers quiet, it was still pretty noisy in there. And then there were fans and everything else to make sure the temperature was maintained at a reasonable, I think 68, 70 degrees. But they had all kinds of sensors on these things. They had cabling, all these things, and they were running them from these massive computer systems that would detect all these different common errors, plus a handful of others that they were specifically looking for. And any signal got immediate analysis. That unit was tested and debugged, and even intermittent problems, then that unit was replaced so that they could go determine, could they find the source of that intermittent problem? And most of the time, not always, not everything they found lent itself to being a fix. Some were software, some were hardware, and so on. But a good many of those things they found were implemented. And I think the big decision they had was, do we stop production or not? Now, one of the issues they did pick up on, and it's called the pick roller issue. And when I first got to Hewlett Packard, I asked about, so how do these things fail? And they all talked about this problem. And it was found in the ORT. The pick roller is a small tacky wheel, basically, that sits just above the paper in the printer. And when you say, hey, I want you to print something, it picks up a piece of paper. And it does that because this little roller, it's sticky a little bit, not too sticky, so it, wraps the paper around itself, but it's just tacky enough that it can start the first page into the mechanisms to get aligned and set up for printing. And so it's called the pick roller. It picks up one page when it's working properly. Well, they found that the issue in ORT is that pick roller in some units, not all of them, stopped picking up the paper. It wouldn't feed the paper at all. And when they took it apart and looked at it and stuff, it was like it was coated in Teflon. It was very slick. And so it would just roll on top of the paper, and not move it forward. So then the printer would say, hey, there's no paper, you're out of paper or whatever. And they investigated it. They stopped production for this because they quickly found out that that rubber-ish material, or some kind of polymer, had an additive that had been there all the time when they started making prototypes of these things that would bloom. So think of it as, if you get a brand new car, it has that new car smell, and it's not a spray that you get down at the gas station. And I don't know if it still does this with new cars. I haven't bought a new car in a long time. But the idea is that polymers that are in your dashboard, in order for them to be formed and shaped and bent and everything else without cracking and all these other phenomena of it, there's an additive that gives it some pliability and some softness to it. But that particular chemical leaches out, or blooms, as it's called. It comes to the surface and dissipates. And that particular chemical, which I completely forget what the name of it is what smells like a new car. That's what we associate a new car smell with, at least some of us do that had cars when this stuff was being used. Well, that was the same additive they put in these pick rollers. Is it allowed them to form it on a roller and attach it to this bar. Now, what they did in previous designs, they used pretty much the exact same thing, but it was the rubber part was made like a gasket separately, and then it was installed on an axle that then got positioned over the paper, and then it was bolted into place. So it had three separate parts instead of one part that was made with this rubber piece permanently attached to it. Well, in the process of changing that design, the manufacturer of these subsystems that did the molding of it needed it to have this additive. Otherwise, it wouldn't adhere to the metal and form correctly and cure correctly, and then have the resulting tackiness. So unbeknownst to anybody, they put this additive in there as a normal course of business of doing molding. And that's just what they did. The question came up, and it stopped production. They stopped making these printers for about a month, and which is a big deal when the production is going to be 1 million per week at one point. And they stopped production, all hands on deck, figure out what's going on. And they had a whole bunch of these units already in the field, being produced and shipped, because it was found about 2 weeks or 3 weeks after it was put on test. And it was in the first batch. And it turns out that if you do product testing, where you print and print and print, and you're just trying to get as much printing through it to exercise all the printing mechanisms and alignment and all these other things, and we print some of the product testing for the inkjet printers just goes through reams and reams and reams of paper per day. If you do that a lot, as this chemical blooms to the surface, it would be rubbed off. It would be sandpapered off, essentially. And so that it would continue to be tacky all the time, and it wouldn't fail, no matter how much paper we put through it. If you don't put any paper through it, and it's just sitting there, it blooms, evaporates off, and it's gone. But if you print, a couple pages per day, which was kind of the biggest user group of these printers that they were making at that time, it's like 10 to 20 pages per day was kind of the scenario. And some were color, some weren't color. It was that sweet spot that it wouldn't rub off this chemical from the surface, but it would burnish it so that it became kind of a very slippery coating on the surface of it. It felt like Teflon almost. And since it was like over half of the population is expected to be in that use case, they decided to stop production. And while they were redesigning the roller and trying to figure out how to get the design right so it wouldn't have this issue, they came up with a kit they started sending out to people that were experiencing this problem. And they were doing it proactively. And very few people in the field actually ever saw this problem before there was a repair or a fix or a treatment available to it. And what they did is they got a little piece of, it was like sandpaper in the shape of a 8.5 by 11 sheet of paper or an A4 page. And they had a little bit of code that would run it back and forth over the pick roller. And it was used as a way to kind of cut off or erase this blooming chemical. And you would run it for a couple of weeks and, every couple of days, and it would solve the problem and go away. And years later, I actually got a phone call in my office at Hewlett-Packard asking for a replacement kit for that, because they've been using the kit on their computer for like 5 years and thought that was how inkjet printers worked and that was required. And I said, no, that was the temporary problem. And luckily I knew about the problem at the time. So the production got stopped. What what they ended up doing, instead of doing a recall of all the units they produced and were in the field, is they made a kit to go fix that problem. And sometimes that could have been a software issue or could have been whatever, and you could solve it as you get the new driver or whatever. But this one needed a mechanical solution to actually use the sandpaper. And customers were actually okay with that. They were just fine. And some printed so much they never saw the issue. Some printed so little they never saw the issue. And a good number of others said, "Hey, the paper's not rolling." And they go, "Oh, yeah, what's your address? We'll send you out this deal. It's a little fix that'll take care of it for you. You run it for a couple of weeks, and um, every couple of days when you think of it, and you'll be fine. Here's what the issue is. Here's what happened. Here's the way to get it going again." And most people were fine with that. It just worked great. Now imagine if you waited until your first million units reached 3 or 4 weeks in production or in use, and you had 400,000 people calling you saying, "Hey, this isn't working," and that's how you found the issue. That would be a problem. And so that's where the value of ORT comes from in a short way. And now it's this, what they were doing was not cheap, and there's no doubt about it. Yet they were able to get ahead of a problem that could have caused a major issue for them, both in branding and market promise and all other stuff, but also in repairs and replacements and everything else that they had to deal with or could have had to deal with. Now, most of the systems I see fall that are actually reasonable ORTs. And this one was a custom system monitor. It was used for safety monitoring of, say, chemical plants and stuff like that, like a pressure vessel. They would monitor it and its inputs and temperatures and cycles and stuff like that. And the intent was to shut down the system safely before that pressure vessel got into a critical stage and may either contaminate product or explode. And so you can see it as a safety process they were using. Now, it's a pretty good size, complicated electronics boxes and sensors and everything else they had in it, but they did pretty decent hazard analysis and risk analysis and FMEAs and stuff like that. And their design team was really focused on, well, what's likely to happen? What are the things that are going to cause this thing to fail? What are the types of stresses that will cause problems for us for this product? And they also included, because their manufacturing engineering and some of their assembly was right in the same building as the designers, so they had that luxury. They regularly looked through, where are all these changes? What's likely to happen? They didn't wait until the supplier says, "Hey, we don't have this op amp anymore. Here's a new one for you." They thought through which components would be really difficult to replace. And if we did have to replace it, what would be the issue that would likely show up? And then obviously it was a guess at the start, not knowing what new component they would do, but they often looked for second sources or third sources for especially critical components to make sure that they had a rational way to bring on a new component without it being a surprise. So they did a lot of stuff right from the start. And a lot of their design work was to have a large margin on all of their components and all of their functionality as much as they could within reason. And so their products were pretty robust, yet their tolerance for a failure was amazingly low. So imagine that if you're monitoring a system so that you can detect before it's about to explode and shut it down safely, and it doesn't work, now you have an explosion. So they took their get it right approach to the designs very seriously, inappropriately so. Well, they set up an ORT in their production line, and they had two sets. One was kind of a burn-in, and it was something they started with when they first started building these products. And the regulatory agencies said, "All right, you do that, you have to keep doing it." And then they took a subset of their boards, not the full systems, but some of the boards, and did more like a life test on it. And it was slightly stressed. It had a little bit of vibration, a little bit of higher temperature, and it would catch, typically, they said early on, it caught production problems. And it was, cold solder or a broken lead or a missing component, stuff like that would show up, and they would go back to their supplier, do repairs on the board and stuff like that. The burn-in caught things early on, but then it rarely caught anything for years. And so when I got involved with them, they were moving to a halt and then HASS screening for their systems as a way to replace both of the types of tests they were doing. But what made them good is that they had a laundry list of very specific failure mechanisms they were trying to detect. And so they knew what they were looking for, and then understanding the failure mechanism allowed them to apply the appropriate stresses. And they found pretty quickly that once they started doing that, and it was kind of in the experimental ways, it wasn't on production, they could identify problems very quickly with very small sample sizes. So if there was a production change, say in the soldering process, they could detect the increase in the variability or the failures that were caused by the increase in variability. Even a very small change in the process, they could detect. But that was only possible because they had done the homework to figure out, well, what specific failure mechanisms are we looking for? And they were pretty good at it. Now, it's not to say that it was a perfect process. They still had failures in the field on occasion. And they use that to feed back into their process to say, how did we miss that on one level? And then how do we make sure we have the process or the vendor components or our design corrected so that we don't see this again? Now, it wasn't high volume and at all. I think they made something like 50 units or 50 systems a quarter kind of thing. These were relatively really complex, custom made, installed systems for, every factory, every plant is different. Number of boilers they had, number of pressure chambers they had, number of caustic soda lines they had, and so on, were always different. And so they would have to customize it a lot, but the electronics was pretty standard. And so they'd been making pretty much exactly the same CPU boards for like 15 years. And so they had the luxury of not having brand new designs every 6 months like the inkjet guys did. But they didn't go into the traditional pull sample off, test it to, in a life test and then throw it away. They were shifted to doing screening because the things they found that they were most commonly discovering were manufacturing related. And HASS is really good at finding stuff like that. And they proved it to themselves, and they convinced the regulatory agencies to drop the benign high temperature running and go to the HASS style of screening so that they could improve their ability to detect failures. And so that was a good example of an organization I ran into. Let's see, Lauren's asking something about when you have a program designed to look for specific failure mechanisms, does that come at the trade-off where you are more likely to miss new failure mechanisms? Yes, that's true. That is very true. They had the luxury of thinking through. It's like, oh, they know they got to go to a new vendor, or the manufacturer is saying, oh, we have to change we've got a new production line. And they had the luxury and the management support to say, we need to totally vet this change before we roll it into production. And in that process, they went through that risk assessment again and saying, well, it's like an FMEA. What is it? How is it possible that this is going to fail? And what are the various causes? What do we need to look for or detect? And with electronics, most of the time, it's temperature, thermocycling, or vibration. And so HASS was kind of lined up right there already for them. Some of the mechanical systems like fans and so on, they did a lot of work as at the component level before they even put it into the systems to make sure that they were in good shape. But yeah, they had the luxury to do this process that they just did on a regular basis, is to look ahead to what could go wrong and can we detect it. And so they didn't have a fixed ORT or HASS profile. It changed as the risk profiles changed. As they worked through different problems and solved them, they would verify it was solved. And let's say it had a power cycling bit to detect that one. They would drop that pending having another failure mechanism that was best detected with power cycling, and then they would add it back in. In the process, they were able to significantly, and they didn't have a lot of field failures to start with, but they cut it at about half. And so for the economics of the situation, they thought that was quite, it was quite an investment in the engineering side, not so much in the testing side, but it allowed their testing to be very specific. And they were seeing great results with it. So they, instead of doing 15 different stresses on it to try to catch all the unknowns, they focused on the vital few, as some of us in these webinars talk about. So it's a good question, Lauren. And it's one where, yeah, you don't know what, sometimes ORT in the testing, like that pick roller, it found something they didn't expect at all. But they had chosen to create a set of stresses that were not accelerated and not, it was just real-time running down to the 5 different use cases and different, I mean, some printers, like I said, printed once a week, that kind of thing for 6 weeks. And they would find stuff because I think one of the stories that I heard was early on, they were running it, and it wasn't clear to me whether it was using a competitor's ink or a third market ink, but there was a particular formulation of ink that if you didn't print a whole lot, the thing would drool, and the little bit of this ink would come out of the nozzle and then crystallize right there. And eventually it would get so bad it would block that port, and it would affect the print quality because not all the nozzles were firing, which led to a formulation change in the ink itself so that it wouldn't do that. And when you first put in an ink cartridge, if you have an inkjet printer, the first thing it does is it goes over to what's called the diaper, actually is the term for the part where it does it, and it spits ink. It blows a bunch of ink out to make sure that, one, everything's working, but two, is that from the time it was produced until you put it in your printer, that no contaminants or drool or all those kinds of things were there. So they kind of do a super spit and blow out the orifice so that make sure it's clear and clean. And then they often recommend that you do a test print to make sure the print quality is all right. And the modern printers now actually do that test print, and they check it itself and makes adjustments for it, like alignment, things like that. Yeah, the one I saw at HB was amazing. It's the be all end all for ORTs, in my opinion, but given their circumstance and situation, it was the appropriate thing to do. And I did talk about it for a bit too long, so I better move on. Let me just mention the absolute worst one. There's a high-end or a high-volume consumer product, and in the product development process, one of the last steps that the development team had to do was list or create an ongoing reliability test and hand it off to the manufacturer to implement. Well, they were already starting to work on the next product, and it was on the checklist, and none of them really knew what ORT was. So one of the guys said, all right, well, we'll just redo all of the qualification tests that we do for the end of development when we say, yep, we meet all our requirements. So they did drop testing and vibration testing, and they did thermal cycling, and they did high temperature, they did low temperature, they did, dust testing, they did all kinds of weird stuff. And it took about 150, 200 samples. And they said, well, we'll do that every month. We'll take samples throughout production for the month, and we'll run it through the qual, which takes about a week to do all of this stuff. It cost about $150,000 per month just for the testing, the lab part of it, and then all the products that they were consuming. And what made it really, really bad is, one, it wasn't focused. It wasn't, use conditions at all. It was, it doesn't meet spec kind of verification testing, qual testing. Very little of them had anything to do with reliability, if anything. And they didn't ever look at the results. Nobody was tracking it. Nobody was monitoring the results of the testing. And things were found. The testing found problems, but it was never investigated. The factory was paid to run the tests, and it was been going on for years and years and years. And so I'm a consultant with him, and I says, do you do, and I heard about this ongoing testing, this qual testing. I said, well, that's got to be a gold mine of information. We could use that to see, which tests are useful and which ones are not. And it took me 2 months to find the data. I was calling all kinds of people, and I finally get a hold of this guy, and he goes, you're the first person that's ever asked for this information. How do I get it to you? It's about time somebody actually looked at it. And I said, how long have you been doing this? He said, 8 years. But the data went back further than that. So their products, every one of the products this team created got qualified every month, sometimes failing, but it had no impact on their organization at all. So I used the data, did a quick plots of the different things I saw. And every time we saw a spike in failures in ORT, about 2 months later, you see a spike in the warranty related claims for that particular product every time. Now, they didn't do great failure analysis on their warranty failures. So I didn't really know whether they were how to relate those things, but it was curious that they had this wonderful data that they really could have made significant improvements to their product because they were overkilling the testing, and it just ignored it. So if you're going to set up an ORT, make sure that somebody looks at it and does something with it, does the failure analysis, does the investigation, and has the authority to, in charter, to go make changes to reduce the chance of field failures. Setting up ORT just to have it checked off your list is, in my opinion, the absolute worst way to go do it. All right, so let's go through some of the considerations here. It starts well before you get to the end of start production. And all of these different things I've listed here, from the FMEA type stuff and hazard analysis and so on, take a look at all of the different failures that your prototypes and breadboards and everything else has failed. Though that's all the most likely things to fail in the field. Not everything that you see in the prototype gets solved. And those things that are intermittent or one time or were deemed too minor to be an issue may just be a symptom for a much more serious problem. So monitoring for them, ORT is a great way to monitor for it, especially when it affects the lifetime of a product. These things are all inputs into what are those things that we need to make sure that our testing can detect. And so it might be a particular test algorithm that you run through your system, or different types of stresses, or some combination of those things, is to figure out what are the areas that are likely to fail. And we do a lot of work in the development process, oftentimes, to identify those things and solve them by design. But we don't get to all of them. And we get to some that we just don't have time or resources to resolve. Those are prime to go monitor over time to see if they show up in any significant way. The other big part is a combination of engineering judgment and margin. So things like HALT allows us to evaluate margin, but we can also do margin testing. We can do power line testing, all kinds of stuff to see how capable is our product versus its requirements. And so look at those in one way to think of it, and we often don't do it. We don't run enough samples and measure enough stuff to do process capability on everything. But that's where the engineering judgment comes in. It's like, for your part of the product, what's most likely to fail? What has the least margin? Where were the design trade-offs? It's questions like that that will quickly give you a list of things to say, oh, these are the likely places to go fail. And then once you have that list, then the next step is, well, how do those risks manifest as failures? And what are the symptoms of that? What are the stresses that cause it or accelerate it? And now you're really close to being able to set up an ORT or some kind of screen or something like that. The biggest problem I see most people have is sampling and sample size. And I'm not going to get into the details of all the statistics and trade-offs of this thing, but it really starts with what level of detection do you need to do? So the inkjet guys are looking at if it's like a 0.5% problem, and I don't remember the exact number they designed it to, then we have to detect it. We have to have a very high probability of detecting an issue in our products that will cause a 0.5% or more failure rate change or of some sort, or an increase in failure rate. And I think their number was actually lower than that. And so they created a sample size that was large enough that if there was a small problem, they had a reasonable chance of having to be able to spot it, to have that failure occur. Right. So the real problem is if you say, well, I don't have enough samples, and you do the math and it says, well, anything that causes a 10% problem or higher, and your product typically runs at 1-2% failure rate per year, you're kind of wasting your time. You may get lucky and find something that's really bad, or you might find something that's very, like a 2-3% problem. But overall, the probability is, don't go to Vegas with those odds. You're going to lose. So if you don't have enough samples, you really need to focus on design to make sure that you have enough margin, enough capacity in your systems to deal with the variations that are going to happen. ORT does take samples, especially if you're looking for a small deviation or a small change. What helps is your ability to detect problems in knowing what you're looking for. If you're just putting products in a chamber, if temperature is the only thing that really initiates the failure mechanisms of most concern, well, then you're okay. But most of the time, that's not enough. That's not sufficient. That's not a good deal. The other half of this is sampling. Ideally, you would do your full sample size every day or every shift or even more often so that you could detect failures pretty quickly. Because if I take, if my sampling is once a week and I'm pulling samples out through that week and it takes me a while to run the testing, I might, like that pick roller thing, they had a month of production on trucks and in distribution centers before they knew they had a problem. Now, if it was a safety issue, they would have done a recall of 4 million units and for that particular thing. So the longer it takes to detect the issues, and part of that is how often you pull samples, is the more of your production is at risk. Because if you detect it here on Friday, you don't know if those issues got built into products on Monday. Now, you may know it from the failure analysis that this component got switched over to this component, or this production change got changed at this date, and you can control it or corral it a little bit better. But it's a trade-off is how, if you find something bad, and it's not a big deal, oftentimes especially if your product's not safety related or fails and creates a dangerous situation, you can stretch that out a little bit, only go once a month or once every couple of weeks. Where if it is a safety issue, And you don't want those in production out in the customer's hands for any length of time with that risk. Then you got to sample more often and maybe use the accelerated techniques to get results quicker, or delay those products from shipping in a warehouse until it's proven that they're safe. Every situation is different. And so the frequency of sampling, how many samples you take, and then what types of stresses that you put on it, and your budget for doing that. Do you have a warehouse size room to run all these tests and staff to do it? If you don't, you're not going to, very likely not going to get much of a result, much of a value from this whole thing. The other part of this is, don't forget that ORT is not limited to just testing a full product. If you've got a power supply that you are most at risk with and understand it's got the most variability in its production or whatever, well, didn't just do the ORTs on that module, on that power supply, and so on. And even better is, like, that good example is they did it before it got rolled into production to make sure that they were stable and they knew what they were looking for in the end of line type testing they were doing. But the sampling trade-off is, ideally you would test everything to failure, but we can't sell many of those or any of those. So we have to take a sample, and sampling in statistics is, what is our probability of detecting what we're looking for? The types of deviations or variations that we want to detect. And the finer that is, the smaller that deviation we want to detect is, the more samples we need. It just goes with the territory. And it becomes a budget issue at that point, right? And that's the economics. There's cost of the samples and the testing itself, and that can be expensive. If that far exceeds the cost of the field failures that could have occurred, and it's not a safety issue, well, then don't do sampling. Don't do the ORT. Just deal with the field failures and pay attention to them and fix them. But on the other hand, if the types of failures you have threaten your brand promise, threaten your market share, or the types of customers, the business you're in, is they say, well, hey, these are bad, we're out of here, and they were one of your 3 main customers. That can be very, very expensive. So it's, what's the risk of some level of failures getting to the field unannounced, or where you don't have a chance to fix it. But part of this whole process is that investment is to give you time to fix the problem before it gets out of control, before it gets, rampant with your customers. It takes time, and you need to have the team available to actually go do it, right? All it's doing is giving you time to go fix it. But if you don't have the resources or the power to go actually make the fix, engineering, verification, implementation, changing suppliers, all of those levels, then what's the point? You can list the problems and watch them appear in the field later, but that's not all that fun. So think through the plan before you, and its economics, so that it actually is a useful plan to actually make a difference with how your production goes through and gets fixed before it gets to the field. So what makes it valuable is, it's thought through from start to finish, and it's customized to your particular product, your particular production line, your particular market. Basic process, I'll go through this pretty quick, is, based on my experience, especially with the better ORTs I've seen, is you really, really need to pay attention to what could happen. What are the problems? What are the issues that will lead to failure? And it's not so much as a design issue. It's more on the margins. Does this signal have enough margin that if we change the capacitor from one value to another value, or go to a different technology of capacitor, will it still transmit the signal? In mechanical systems and alignments and all those other things, if the alignment variation goes off on a fan, it's likely it's going to wear out quicker. So how stable is that alignment? and thinking through what are the things that are going to cause that to have a problem or go wrong. And as I mentioned earlier, it's thinking through the FMEAs, the hazard analysis, and using those information, one, to fix your design as you're going through the design process or setting up your production line. But two is use that as information to build out your, if you're going to do ORT, what are the things we're actually trying to detect, and how do we go about detecting them? But it's a continuing process right from the start of the design and development process, one for the benefit of the design, one for the benefit of production, and also with your vendors. But you can also work with them to say, what have we missed? What are the things that could get through? What are the things that we're not fixing yet are likely to occur? And that's your source of starting the planning of an ORT, is to look for those things. Now, to Lauren's point, is that in that process is still going to be surprised. Yet the idea is that many of the stresses that we apply to a product in the areas that we have unknowns of, is this a big enough issue for us to go fix it or not, like temperature, vibration, power cycling, things like that, will often also excite other things. And if you're running your ORT at use conditions for long enough, the chance of finding something like a pick roller problem that was completely unexpected certainly could happen. So a couple different parts to it there, but it's the narrowing it down is, it's, I think that correlated to that is it's impossible to design a test to catch everything. And I think the most practical way to do it is run your product in use conditions in various ways that your customers are going to use it in real conditions and real, not accelerated at all, and run them longer. It just gives you time. If you start your ORT before the products get to your customers, that gives you a lead time, and that's the best you can hope for. There's plenty of statistics out there. Sample sizes is one of them, but that's not the end of the deal, right? You really need to think about, well, how am I going to detect when it's not working? And you have the option, especially in the lab, to put on all kinds of extra monitoring systems so that you get full logs, you get whole bunch of diagnostics. You can, instead of the printer just stopping, for example, it gives you a crash report. Why? Right. And it may take some special software, it may take some special cabling, all separate monitoring, all that other stuff. It adds to the complexity and cost of your testing, yet it makes the ability to diagnose and troubleshoot and get to the root cause much quicker. And you're racing against the clock in ORTs. Is oftentimes your samples have already shipped, or the other parts of that production that you didn't sample are already out to customers. And so all you have in your testing is a short lead time, depending on how long it takes your product to get to customers. Right. But have the ability set up so that you can detect issues, get the resolution quick, do the failure analysis as quick as possible to true root cause, and then go fix it. And you can do short and long-term fixes. But the plan should also be very clear, is that this kind of issue, say safety issue, is stop production, or some threshold of failure mechanism is stop production, or what's the trigger when we consider doing a recall, and what are the thresholds that trigger these things. And they can be adjusted at the moment, obviously. Yet the idea is that the plan includes, when do we hit the stop button, for example, and then go fix it, go solve the problem, resolve the issue. You're wasting time thinking through that after you find the problem. And so it's think through all of those and make it part of the policy and part of the product of the ORT plan, and with the appropriate management teams, so that they have a clear idea that, oh, this issue rises to this threshold and we got to deal with it. The final part of this thing by far is, if you find something and you don't do anything about it, well, you're not really doing ORT. You're just kind of watching your product fail or not fail. It's not terribly useful. But take a look at like a basic fracas system. Is we find stuff and we track them to a short-term solution, long-term solution, and then we verify that it actually worked. And then we have to come back and do it again. But if you set up a bunch of testing and don't ever monitor it or think about it, well, that's just a waste of money. There's no doubt about it whatsoever. And the final line of this is, in the plan, know when you're going to stop it. It doesn't make sense to sample products that you're no longer ever going to change. It's out of date. It's archived. We're not doing this anymore. And we're making products as replacements for anybody that complains anymore. We're not even selling them anymore. Doing ORT on those things is a waste of time. So think through what triggers you to stop the testing, because otherwise it'll be like that group, that the worst one I saw, where they ran them from years and years and years without ever thinking about it. So that's the thought here. Last question for you is, will this work in your organization? Maybe, maybe not. That's for you to answer, not me. There's plenty more resources up on Accendo, one place or another. And if you have questions about it, you can let us know. We'll probably get back to you as quick as we can with some either other ideas or resources. But it's hopefully this presentation here gave you a few things to think about as you consider implementing an ORT on your product lines. Or maybe I just scared you away from doing it at all. So few people are heading out. You're very welcome. Thanks, y'all, for participating today. Yeah, Carl, you're talking about cultural reliability starts with the mission statement. Yeah, I agree with that. But it's also celebrating failures. I would add that to your note there. Let's see, got a couple new messages. People are peeling off. Welcome, Marcello. Yeah, lots of points to ponder. That's the idea. I mean, if it was the simple formula, we wouldn't do a webinar on it, right? If it's, but even a hypothesis test is not straightforward when you start thinking through it and what makes a good one versus not. Also,